So hello everyone, I'm Nathan. You might know me online as NPC Dev. And today I want to tell you about a technique for controllably generating maps or levels and a specific experimental tool called GroundCollapse that I'm hoping will let designers get their hands on this technique and really start making cool things with it. So where am I coming from and why am I excited about this stuff? Well, I was working as a game engineer at Turbine here in Massachusetts, and then I got particularly excited about how procedural content generation and AI could create specific, unique experiences for players. So I went back to academia to really focus on that. And now I'm a PhD candidate at Northeastern University. I'm co-advised by Dr. Maggie Saiful-Nasr and Dr. Stacy Marcella. And my research really focuses on creating AI-enabled co-creative tools to meet the needs of game designers. So I've got another project that there's a little screenshot here, Evolving Behavior. I'm happy to talk to you about that as well sometime in the future. So I'm coming at this from the goal of really building things for game designers and then seeing what we can do with cool AI tools. So what do I mean by computational co-creativity? So it's a type of human-AI interaction where people are collaborating with AI-supported tools to make something creative together. And I think that constraint-based PCG, which I'm going to talk to you about today, might be kind of a good angle for this in one particular domain, or maybe several domains, but generally in the domains of generating maps, levels, or other types of content that need to be kind of carefully controlled, and the designer has some particular requirements for that they can kind of clearly state. So I'm going to note that a lot of this isn't going to be just my ideas. So this isn't like I'm presenting my cool work that I did. There's going to be a bunch of stuff in this talk that's explaining what other people have come up with. And there are a bunch of other people working in this kind of area. And I'll mention some of their work later. I also don't have all the answers necessarily. This talk is going to be kind of an early stage-ish thing. I'm still fairly early in exploring the space. The tools and techniques I'll be talking about are really just a starting point for a bigger exploration of this area. So I'm really hoping to get you all interested in this topic and get you thinking about ways that you could use and build on these techniques and on the open source tool I'll be discussing today. So that's why I want, if you have questions or if you have ideas during the talk, feel free to come up and ask them at the QA spot. The constraint-based PCG techniques I'll be talking about today are very related to and inspired by something that I think more and more people are trying out in games, which is this particular generative technique called wave function collapse. And you might have heard the term because I think it's kind of gaining interest in a lot of game design and especially map design kinds of communities. But if you haven't, that's fine. We'll talk about it. So wave function collapse is very, very loosely inspired by the ideas of quantum mechanics, more of kind of a marketing thing than a real physics thing. But it's kind of inspired by this idea of superposition, where you have a bunch of different possibilities and something could be in many different possible states, but then you collapse that set of possibilities into a single final observed result. And essentially in wave function collapse, you start with a whole map or image or whatever you're generating that every spot in that image or map is kind of able to be in any possible state. And then in some particular spot, you pick one random state and collapse it to that specific state. So you've taken all those possible states for that one spot and picked one and set that spot. But that leads to some restrictions on what the neighboring states could be, because probably you have some rules about, what can be next to what in the image. And so those neighbors need to make sense next to that collapsed spot. So you can then pick one of the smaller number of reasonable states for a neighbor that has more restrictions now, and then keep going and expanding out from there until you've collapsed the whole space into one final result. And so you've basically observed a single possibility out of all the possible maps or images that you could have generated. And you can get different results by randomly changing choices you made along the way. And there are two versions of wave function collapse. There's the overlap model and the tiled model. We'll mostly talk about the tiled model today, but briefly, the overlap model is usually used to generate variations of an input image. So from some example, you extract possible patterns of valid pixels in overlapping different rectangles of the image, and then you use those patterns to figure out what valid neighbors are for each pixel when you're generating the final image. Now, if you had some sort of mapping of pixels to some sort of tile or level element, maybe each color is one particular tile type, then you could imagine generating levels this way, not just images. But the tiled model is the other option, and I find it easier to use with a tile set where you want to kind of pre-specify the valid neighbors rather than trying to learn them from some example images. So if you know, I have these particular tiles and they need to connect in these particular ways, then the tiled model can be good for that. So you basically tell wave function collapse which tiles should or should not go next to each other, and it will respect those rules when building the level. And we're going to focus on that tiled model today because that way designers can control the exact tiles available and how they're allowed to connect to each other. Now, this does require a manual setup of those rules for neighbors, but it doesn't require you to construct example images to show every possible combination in your generated maps. Now, wave function collapse has been used in real games, and there's also a bunch of cool extensions to it out there. For instance, it's been extended to 3D. It's been integrated with pathfinding to make sure that the final map can be navigated. It's been extended to work on arbitrary graphs that aren't grids, and more. And I'll show a list of references to these particular things that I'm talking about at the end. You can also contact me later for links to this kind of stuff. So how does wave function collapse work in detail? So here's the process. And yes, as Aaron says, Oscar Stolberg is a game designer who uses wave function collapse in really cool ways and extends it in interesting ways. So check out Bad North. It's a game. Anyway, so how does this work? So here's the process. The basic concepts aren't particularly complicated. So you basically start with all the options available in every space in the map, as I mentioned earlier. And then in a loop, you repeat this process where you pick the spot that has the fewest remaining options. You use a weighted randomness or some sort of method to select one of those random options for that spot. And then you have the tile at that particular spot, and you're basically saying that will be the correct tile there. And then that limits what the neighbors can be based on your rules for how neighbors can be next to each other. And so now you have fewer options for the neighbors of that tile because they need to connect. But that also means that you probably have fewer options for the neighbors of those tiles. So you go out further and you realize that probably you've limited a little bit what can be around the neighbors of the neighbors, right? and so forth. And you just propagate all that information outwards. And then once you're done updating all the correct tiles, then you repeat the loop and you find the spot that now is the most constrained, that has the fewest options left. And then you repeat. Now, this thing that wave function collapse does that's clever, that I just mentioned, is how it picks this minimum entropy spot or most constrained spot to collapse next. It's the one that has like the fewest options and is the most limited. So let's think about why that would be a good idea. Let's imagine that one spot has only 2 possibilities left and has a neighbor that also has only 2 options left. Now, based on the rules, we know that there is some way to select those options so that they will work next to each other, because that's how we've been limiting the neighbors. But that doesn't mean that all the possible combinations are valid. Maybe the first option of the first tile only matches the first option of the second. So option 1, and maybe option 2 matches option 2, but 1 doesn't match up with 2. So let's say that we leave those alone, we don't collapse them immediately, and instead we kept selecting other tiles to collapse around them. Now maybe we end up limiting option 1 on tile 1, and we end up limiting to option 2 on tile 2, and they don't actually match together. So now we have no spot or no valid tile choice that would work for these 2 tiles. So we've created what's called a conflict, a case where you can't actually select a valid tile for a spot. Now, if we had chosen to collapse one of those 2 more constrained tiles first, we probably wouldn't have had this problem, because we would have resolved the other neighbor to the only valid option that it had left. So this clever method of collapsing tiles first makes it less likely to cause these kinds of problems for yourself later. But even with this clever choice of which tiles to collapse first, it is still possible for wave function collapse to run into a conflict. And maybe it somehow ends up with just too many constrained tiles at once, and you couldn't pick something simultaneously for everything, and eventually it causes a conflict. In that case, traditional wave function collapse just starts over from scratch and hopes it doesn't run into that same problem next time. So that might be slow, and there are some modifications of wave function collapse that backtrack, and when they find a conflict, they make some different choices earlier to hopefully resolve the conflict and then go back forward. Now, this problem can become even worse if you add things like pathfinding or other requirements on top of wave function collapse that could further constrain which tiles are valid neighbors. For example, what if you don't want a particular tile to repeat within 3 spaces of itself? Now, changing the selection in one place could impact tiles 3 jumps away, and those requirements could impact tiles even 3 jumps away from that, and so forth. Now, you can see how these kind of additional long-range requirements could kind of lead one change in one place to cause problems further down the line elsewhere, and might make it more likely that some serious conflicts will arise. So at some point, if you make all this more and more complicated with your rules, even with backtracking, you're basically talking about solving a complex system of interlinked requirements. And this is actually a problem that computer scientists have worked on solving for a long time, kind of in general. It's the domain of constraint solving. Fortunately, we have this long history of constraint solving to draw on here. And there's also examples of constraint solving being used in games. You can think of constraint solving as a form of declarative programming. You declare what you want the output to be, and you let the constraint solver figure out how to get there. It's basically just, here are the rules, now make something that doesn't violate any of those rules. And there's this really cool paper from Carth and Smith in 2017 where they show that we can think of wave function collapse as a form of constraint-based procedural content generation, where you specify the rules for neighbors and require that all the tiles are selected so that their neighbors are still valid, and then you let the constraint solver resolve the problems. So basic wave function collapse doesn't use a very powerful constraint solver. It just restarts if it violates the constraints. And some extensions, such as backtracking, are essentially writing a more powerful constraint solver. But they're very specific still to the particular problems of wave function collapse, which has some benefits because it's easier to write. And as Aaron said, building a recursive constraint solver could be a lot of work if you do kind of a general solution. And it might be faster than a general purpose constraint solver. But there are these drawbacks in how hard it could be to add additional rules. Like if you did want those kinds of long-range constraints, it might be hard to modify your wave function collapse solver that you wrote yourself to add those kinds of extra things. In games, researchers have used constraint solving to do things like creating mazes and puzzles, designing solvable levels for platformers, and they often specifically use a form of constraint solving called answer set programming. Answer set programming is basically, we'll call it ASP, is basically a constraint solver that has a nice way of specifying starting conditions and constraints, and then generating various valid possible solutions or sets of answers. And because it can produce a bunch of random but valid solutions, it can be really nice for a PCG, where you want to generate a variety of results from your overall possibility space. And again, if you would like exact references to all of these things, you'll see some at the end, and I can also send you them later. There are various answer set programming solvers out there. For the project I'm talking about today, I use Klingo, which has a pretty long development history and a pretty good set of features. It uses a declarative programming language called answer set prolog, ANS prolog, to specify the constraints and conditions. And it has a bunch of cool extra features like soft constraints, which attempt to score and optimize the solutions towards a particular condition, but they don't completely throw them out if they're violated. They just try to get as close as possible. And then numeric constraints, which can set minimum and maximum values for things, and various other cool features. And you can run Klingo as a standalone program, or you can use it in a library, as a library in Python, C, and C++. So it can be easily integrated with other tools. So how does ASP work? ASP needs to know that particular things are true. It needs to know what concepts exist in this problem space that you're creating that it needs to be solving. So you write particular things as facts by writing them down with a period at the end. So for instance, this one says dim is a thing that exists, and dim1 in particular exists and is a dim that has the value 1. You can create a whole range of facts with various values at once using the 2 dots operator shown there. So you could say that everything from 1 to whatever width is, those are dims. Then you can make rules, which are facts that are implied by other facts. So in the example here, if there's a dim with value x and another dim with value y, you're saying there is a cell that has value x and y. So the way that this is written, we're saying that for every combination of dims, we're essentially creating a cell. Now, we want some solutions to the problem to be invalid. So we want to constrain the possible answers, right? So for that, we use constraints. These are just like rules, except that they have nothing on the left side. You can sort of think of them backwards from a rule. So we're not saying we're creating something we want to be true. Instead, we're essentially telling answer set programming a thing we don't want to happen. So you can think of this as saying, in this case, if the right side is true, then it implies that nothing is true. We've created basically a contradiction, an impossibility. So in this case, it's like if x is less than 0, it can't be a dim. We can't have a dim where that's true. There's some other really nice extra features of Klingo and ASP that we don't have time to explore fully right now. But one important one is that you can set range limits for constraints and other rules. So you can require, for instance, that there's between 1 and 10 of something. So in this case, you're saying between 1 and 10 of the existence of a dim with some values. So there must be at least one dim, there must be no more than 10. And because, remember, the constraints are sort of inverted, we have to say we are violating the constraint if there's not between 1 and 10. So we can make sure that, there's not too many, or they don't get too long like these cats. So let's get more specific about how we use answer set programming to re-implement wave function collapse with general constraint solving, and then extend it with many other constraints. So we'll talk about this in the context of my experimental tool that does exactly this, called GroundCollapse. GroundCollapse uses constraint-based PCG to generate infinite maps or terrain in 2D. You can make your own tile set and integrate it with a game to generate levels with tiles that will be guaranteed to match up next to each other, and with other custom rules you might want to add. GroundCollapse is written in Python, so at the moment it would be easiest to use if you either have a Python-based game or a way to call Python code from your engine. But if you don't need generated levels to be generated at runtime, but you want to instead pre-generate content, you could also use the tool standalone, generate the levels ahead of time, save them, and then load them in your game regardless of what language it's in. Aaron asks, are the big squares appearing here tiles, or are they made of lots of smaller tiles? So in this case, these are made of lots of small tiles. So each of these bigger squares I'll call a chunk, kind of like in Minecraft or another game that generates chunks of content at one time. So each tile there is like one tiny little like part of the squares. So here's the basic answer set programming code that essentially does wave function collapse. It's really not very long, and we'll go through it. So first, you need to tell answer set programming about the size of your map to generate, or the size of your chunk, in this case, to generate. So we can provide this input parameter that we'll call width, and the code that calls this answer set programming code can pass in that width parameter. Next, you tell it what a tile or cell means in that space. So just like we saw in the previous slides, we say a fact that a dim is anything between 1 and the width, and a cell is 2 dims together. And you could extend that to 3D, right, by adding like a z coordinate there. Next, you define what cells are adjacent to each other. Are they neighbors, and in what directions? So you have to say 2 cells are adjacent in a particular direction, dx, dy, if they're both cells, and the difference in their x coordinates is dx, the difference in their y coordinates is dy, and in this case, we're going to constrain this particular rule for adjacency to be that the dx is exactly 1, right? So we've moved exactly 1 cell left or right, and dy is exactly 0. And then you would make a similar rule for dy being 1 and dx being 0, so that you can have neighbors vertically as well. And you could do that for diagonals, right? You could say dx and dy have to be exactly 1 or -1. So this is how you set up, here's what a neighbor means, or here's what adjacency means. Finally, you can add constraints. So in this case, we're saying each cell needs to be assigned exactly 1 tile at the final solution of this, right? So we're saying a range constraint where there must be 1 assignment of a tile type P at every XY cell. And then we do the wave function collapse rule for neighbors. So after we assign any particular tile, the neighbors in each direction still need to have at least one legal assignment left, right? We can't make it so that they now have no way that they could assign a tile. So we're saying if two cells are adjacent and there's an assignment to one of them, then we need at least one legal assignment to the other one. Or we're saying if there's not at least one, then it's a violation of the constraint. As a note, because we're using this general constraint solver, we could actually just replace this rule with something simpler, which is that the final assignment to the tile has to fit with the final assignment to the neighbor. Instead of like, there must be at least one legal one, you could just say, if two tiles are both assigned, they must be still valid. And you could let the constraint solver sort out how to get there, because we don't actually have to say, oh, you need to look at your immediate neighbors because it's a constraint solver. It just generally needs to solve all of the possible constraints in the image or in the space. So it wouldn't be exactly how wave function collapse checks validity by collapsing neighbors, but it would still require that the whole thing needs to be valid at the end. But how do we let answer set programming know which tile types exist and which ones are allowed to be next to each other? We don't want to have to like type all of those tile set rules manually in the code. And in fact, we don't want this hard coded at all. We want to define the tile set in some data file and then kind of augment our program with that information. And we can do that by adding extra statements to the program from Python when we load the tile set data. So you don't have to type it all into the original ASP file. You can actually, at runtime, add statements from Python or C++. We're using Python in this case. So we can add facts that tell Klingo which types exist. So that's that first tile statement part there. And then we can add rules for which tiles are legally allowed to be next to each other in various directions. So that's the second tile adjacency statement part there. So you're saying it is legal in this particular direction for this tile type to be next to this other tile type. And you add these from the Python library to the program and reparse using parse program. And then you produce a final program for your tile set. So before I go on to more ASP soft constraint stuff, are there any questions so far? All right. If you do come up with questions, feel free to just step into that QA spot and ask. Okay. So now that we have the basic WFC, we can generate valid maps. But what if we want like some specific aesthetics? Well, because we're using answer set programming, we can do that without changing our constraint solver. So for instance, if we want to make sure that there's a nice variety of tiles in our map, not just the same tile repeated over and over, we could add soft constraints that encourage that kind of thing. So for instance, we could count how many times each tile type is used using this first statement up here. And then we could say we want to minimize the number of times each tile type is used, so that we're basically saying don't use the same tile over and over if possible. Now this won't like prevent the map from working at all if it's violated, because it's a soft constraint. It'll just kind of tend towards the solutions that use fewer tiles of the same type. Or we could minimize unused tile types. So we try to make sure that every tile type appears at least once. So you can see that these kind of soft global constraints can encourage variety and create different kinds of maps. And there's many more possibilities, right? We could add weights for each tile type to encourage some types of tile to appear only rarely. Maybe there's some special tiles that we don't want to have very often. We could put hard caps on some types of tile and say you can never have more than 2 of this tile. Or you could even do that on like combinations of tiles. We could encourage tiles that are like walkable empty space in our game to be clumped more together so that we get large open spaces. We could do all sorts of stuff. All right, so now we've talked about generating some particular single chunk of terrain, but as all of these chunks get bigger, the cost of solving all these constraints could also get really large. So how do we generate large maps or infinite terrain? Well, one way would be to generate one chunk at a time and set constraints around the edges to make sure that they match up. So you'd essentially expand the chunk by 1 at the edge, make sure that those edge tiles that are kind of outside the main part of the chunk are exactly what's been generated for the neighbor chunks. And then when you render the whole chunk, you would just drop those edges that are redundant with the neighbor. And that's how I do it in GroundCollapse. Now, a downside to this is that it could lead back to conflicts. So we're kind of losing some of that power of the constraint solver to backtrack and resolve issues when we say, okay, this chunk is done, we're throwing out all the constraint stuff, we're moving on to the next chunk. So with a fairly flexible tile set so far, I haven't run into too many issues with that. So if you have a tile set where most things have some valid neighbor, then you can probably make sure that the chunk edges are likely to match okay. But your mileage may vary, and it's going to depend on the flexibility of your tile set. So further research should probably look for better solutions that can provide a good trade-off between quickly creating map tiles versus keeping this constraint solver involved so that you prevent conflicts. So maybe there's some sort of hierarchical solving you could do where you generate some higher level layout for the space that you know your tile set can work with, and then generate the individual tile details somehow. So maybe you do like constraint solving on a general level and then on a specific granular level. Or maybe this will just go away as a problem as we get more and more computing power and better constraint solvers are developed. We have maybe like a GPU-based constraint solver that's super fast or something. And maybe we end up allowing much larger chunks, and you don't even need like to worry about many, many different chunks. So this is definitely a place for more research. And there's another catch here for performance. If we want to generate separate chunks, we need to rerun the constraint program for every chunk, right? But each time we change the program, we have to do something called grounding it, which is basically like compiling in another language. You're converting the kind of complex range and rule statements and stuff into individual simple little facts and constraints that the constraint solver can do. And it does this automatically for you, right? But it's still kind of an expensive, slow process to ground the program. So we don't want to reground the whole program for every single different chunk we need to generate. But we do need specific information about the edges that we want to match up with, right? So how do we avoid regrounding every time? Well, fortunately, Klingo provides something for this called externals. So how do externals work? We can basically use these to say that there could be a fact that exists, but we can change at runtime whether it is true or false. So if you say there's an external of a cell, then you're basically saying at runtime, I'll tell you whether this cell is actually there or whether it's not actually there. So here we're basically adding external optional rows of tiles around the edge of the chunk, like I mentioned. So if there is some other chunk in a particular direction that we have to match up with, we can set those externals to be true. And then we can use the force rule that you see here to specify the exact tile types of those cells on the edges so that we will invalidate any solution that doesn't have that exact tile type at the edge. Now we could also force interior cells. So this could also be used to like pin one particular tile to one particular spot in the chunk, which we'll talk about using later. So does that make sense for folks in terms of how you would make sure that you're matching other chunks, but you don't have to like reground the whole program every time? Cool. So let's put the code aside because we've basically gone through all the standard stuff. But now we need data, right? To generate a map, we need a tile set. So the tile set needs to tell the tool how to draw each tile and what neighbors are allowed for it. You could like learn this data. You could provide it in various ways. But right now we use a JSON text format to define the tile set. And I like JSON and text because it can be edited by hand, it can be compared and merged, versioned easily, etc. So there's a couple options for how to define your tile set. The most basic option is to give a list of all the other tiles that are allowed in each direction. The current version of GroundCollapse only worries about the 4 cardinal directions, not corners. For most tile sets, that's fine, because if you constrain both of the 2 edges, then probably the corner will match. But if your tile set doesn't work like that, you could easily extend GroundCollapse to have all 8 directions constrained. Now, you can also, because defining every valid neighbor relationship with every other possible tile could be a lot of data and very time-consuming, you can also use edge tags. And you can basically think of those as like the types of neighboring edges allowed in that direction. So if one of those tags matches the other edge on the other tile, it'll be allowed in that direction. So for instance, you might tag a tile with like blue top on its right edge, and any other tile with blue top on its left edge could be placed next to it on the right. You might also have cases where tags lead to some not great looking combinations. Like if a tile has the same tags on its own left edge and right edge, but you don't actually want that tile to just keep repeating next to itself. So to solve this problem, you can specifically mark individual tiles that you never want in a given direction, even if the tag rules would have allowed them to be next to each other, using the never adjacent keyword. Finally, there's this file format for the tile set allows various extra kinds of data. So there's built-in keywords for walkability. Can each edge of the tile be walked through? But you can also have this kind of extra data section where you can put basically arbitrary JSON in there, and then it has methods for passing that on to a game-specific parser. So you could use that for things like particular monsters spawn on particular types of tiles, or particular loot spawns on a particular type of tile, or you need an extra shader or a particular sprite or something to add to that tile. But even with all this cool fancy stuff like tags, it can be very time-consuming and error-prone to construct all the possible relationships in a tile set in a text file. Right? It could be tough for you to even think about and visualize how the tiles would connect and remember which sides of the tile mean what and which tag you're using where. So GroundCollapse has a visual tile set editor to help you quickly build new tile sets. The tile set editor provides some nice features like undo redo support, visualization of each tile when you set the constraints, and so forth. It's written in Pygame using the Pygame GUI library. You can select and slice a part of a sprite sheet, and that automatically creates new tiles from the images in that area of the sprite sheet. You can also manually set up individual tiles at particular coordinates and just extract one tile at a time from the sheet. Or you can use separate image files and not use a single sprite sheet. You can then open a particular tile and set its constraints. So you can work on one edge at a time, and visualize how the other tiles might look next to it. And then either individually select the allowed tiles, or you can type in tags for that edge. And if you use tags, the editor will show you which other tiles are allowed as neighbors due to that tag. And then you can specifically prohibit ones that don't look right. So here's a video showing a slightly earlier version of the editor before I added those tags and prohibited adjacencies. You can see how you can preview each possible neighbor of a tile and then set which ones are allowed to be adjacent. And here's a video showing how you can add and remove tiles, use undo and redo to revert that, and then let you edit and preview tags and prohibit individual tiles even if their tags match. And then here's a very sped up and edited for brevity video that illustrates a complete workflow where you might add some tiles sliced from a selection of a sprite sheet, a section of a sprite sheet, set their edge adjacencies using tags, and then generate a much more complex map than you could have made with the smaller tile set that you had before. Finally, as you test your tile set, you may find cases where GroundCollapse runs into trouble with your current tile set and rules. You can use debugging modes to figure out what cases are giving it trouble, and then add tiles or fix rules to let it fill those types of spaces in the future. There's probably a lot of good debugging stuff that we could do beyond this. This is just what we have right now, but it's, you can see where the holes are, see where you don't have a tile that fits that space. So what's the result? You can create many varied and interesting patterns. But the tile set matters a lot, right? And which tiles are available can drastically change things, and also can create these cases where you need to debug and it doesn't quite fit. So there are a lot of improvements that we could make to help designers define constraints to control the variety and style of the resulting levels. There's a need for more tutorials and documentation and learning flow that would be helpful for folks who are new to the tool and haven't seen this presentation and don't really know how all this constraint stuff works. But in its current form, GroundCollapse is available on itch for free. It is possible to make a full tile set and play around with the results. And you can freely modify the code. The code's available, and you can integrate it with your own projects. So here are some GIFs that show how the space can generate and regenerate itself. So I'm kind of interested. You could use GroundCollapse in many ways. You could always save every chunk and make sure that they're the same when you come back to it. But I'm kind of interested in this idea of a dreamlike space where you can leave an area and then come back to it later, and it's not how you remember it. It's different. And I made a small prototype of a game to kind of show this unique potential of constraint-based PCG and GroundCollapse to do that kind of thing. So it's called Dreams of Collapse, and it's a roguelike set in an infinite dream world that changes around you. And you can also change the dream space yourself as the player by destroying part of the world and causing it to regenerate itself around you. This project uses those custom properties I mentioned earlier to spawn monsters on specific tiles and ensure walkability in particular spaces. So for instance, we make sure that the player is on tiles that are walkable. So when they regenerate the world around them, they can still move, right? And the guarantees of constraint-based PCG and GroundCollapse allow us to do this, right? They allow us to let the player destroy and regenerate part of the world with the confidence that it will still match up to the surroundings. So I'll show you a little trailer for the game. It's It's just a prototype, so it's not particularly pretty or finished, but here you go. All right. So I made this prototype in 1 week for the 7-day roguelike challenge. So you can see that, it's not incredibly hard to use this tool. You can make some stuff that's kind of neat pretty quickly. And you can also download this prototype on itch. It's free. The code's available. So you're welcome to use it and modify it and see how to work with GroundCollapse. So what else can we do with constraint-based PCG in the future? Well, there's a lot of cool things we could think about. So what if we let the player pin or remember various parts of this world to ensure that they stay reachable? They could maybe build a home in shifting dream space. Or what if we shift the likelihood of various tiles to appear over time? Maybe we could slowly change which biome you're in, or reveal hidden content, or increase the difficulty as the player gets deeper into the game. You could probably even let the player place specific tiles, maybe almost like building in Minecraft or something, and then regenerate nearby areas to seamlessly integrate their creation into the space. There may be many other possibilities that I haven't thought of. For instance, if you didn't want to regenerate stuff all the time and you wanted to just have a fixed space, you could do that. And there's probably a lot of other stuff that I haven't come up with. So I hope that you'll think about what else you might want to do with this sort of tech. There's also a lot of things that we could do for usability and designer assistance that are intriguing areas for future research. So we could study, what do designers find difficult about defining constraints? Is it syntax? Do they find it hard to reason about how constraints will interact with each other? Do they need kind of visual tools to build these constraints, or some kind of expressive language that they can use to build the constraints? Do they want visualizations or suggestions that are maybe informed by AI analysis, or some sort of automated testing or error detection or learning of constraints, or so forth? And here, as I mentioned, the references that I've talked about, people who've written about this before. As I said, a lot of this is not just my work. It builds on all of this stuff that other people have come up with. So I didn't come up with wave function collapse or how to use answer set programming even for wave function collapse. So please do check these out. I'm also happy to send you links. Feel free to contact me on email or Twitter. Happy to talk about this stuff. And I'd also like to thank my advisors, Dr. Maggie Saif-Al-Nasr and Dr. Stacy Marcella, for their support. And thanks to Dr. Adam M. Smith at Santa Cruz, who did a lot of answer set programming stuff and gave me advice on it. And along with Isaac Karth and Dr. Mark Nelson, they created this kind of basic example code that I showed you at the start for how to do wave function collapse in answer set programming. And I'm using that code with their permission. So thank you so much for joining me for this journey through Dreamspace. and I hope that you will now take over to come up with your own cool ideas for using this work in the future. So what questions and ideas do you have at the moment?
Hi, as people can probably guess, I have 1,000 questions.
Excellent.
I guess my first one was, you had mentioned that you moved to answer set programming from the original, standard wave collapse, uh, to make it. You were pointing out a bunch of things that weren't working well for wave collapse. And I'm like, okay, let's use cling out. No, obviously works quite well. Like your solution looks super cool. Did it end up being faster? Was it more reliable? Do you have any thoughts on the runtime between them? Like, because it seems like if it's not recursing, you still have to run it and hope that it works. And if it fails, run it again. What do you think about the pros and cons of the two?
Yeah, thanks for that question. So I have not actually used the original wave function collapse for any particular game. So I can't easily directly compare them from my own experience, but I can say that using a full constraint solver like answer set programming will definitely be slower in general than just using standard wave function collapse, where you assume that everything will be fine and just keep running, because it does have to like create all of the possible constraints and possibilities, test which ones are valid and stuff like that. And it's not designed in such a streamlined fashion for just this one particular problem. So that's why we need to do things like generate fairly small chunks and connect them together rather than generate one huge level all at once. Because as you get more and more space for it to deal with, it has to deal with more and more issues. So as constraint solvers get faster and stuff, that'll become less of a problem. But definitely there are some trade-offs of using this general constraint solver in terms of speed. On the other hand, we can now do things that you could never add to wave function collapse without this powerful constraint solver, right? So if you tried to do things like have these like long range rules about like, well, you don't really want the same tile within 5 tiles of here, or like we want to maximize the number of different possible tiles that you can have in the space, it would be very hard to implement that with standard wave function collapse without running into huge numbers of conflicts. So we're basically trading off speed for flexibility and the ability to really guarantee that we're not going to have to like restart and backtrack constantly.
Awesome. That's super cool.
Thanks. Other questions, ideas?
Looking at your generated ground sets, it looked as if you were generating disconnected walkable areas. That is, you'd have one walkable area and then another that couldn't reach it from, that you couldn't walk to from there.
Yes.
The idea of not having disconnected walkable areas, of having them all connect, is a constraint, but it's not a direct edge-to-edge constraint, or so on. Did you ever try to program that constraint?
Yes, thanks for that question. That's a really good one. So I have not yet tried to generate a level where the whole level is like connected, but that is something you can do with a constraint solver. You can, other people, and I think Carth and Smith show it, or Nelson and Smith do, but there's other people who've shown that you can basically enforce that there's a path from one place to another in a level that you generate this way. Or you can like enforce that like all tiles of a particular type are able to be reached from each other. So that's certainly something you can do. Now the chunk-based infinite generation that I'm doing makes that harder, right? Because you don't have the constraint solver working between chunks. So it's a little harder to know how you would generate a path that's guaranteed to match up between many different chunks, right? But that's where maybe this hierarchical constraint solving might come in. So maybe you generate a valid path through your space first, and then you require that those tiles be walkable when you generate the, yeah. And as Aaron says, you might be able to build these higher level constraints either outside of ASP or do a kind of two-stage process where you do a higher level ASP to solve the general path that you want, and then lower level ASP to tile it with specific tiles.
Okay.
So it should be doable in theory. Does that answer the question?
Yes.
Awesome, thanks.
Hey, can you guys hear me?
I can hear you, yeah.
Cool. So when you and Aaron mentioned recursive, does that mean that it is like going back and starting over, or going up like one step after like looking at soft constraints? Is it potentially doing like, hey, this is getting to like a good solution, and you know, maybe it's using like a hill climbing algorithm or something to say like, hey, it's getting better, it's getting better. Oh, I hit a block. Let's go up one and see if it could have done that. Or like sometimes accepting like a randomly worse situation in order to kind of not find the same thing every time. Is it like kind of going up and down by small steps, or is it only like kind of restarting?
That's a really good question. So answer set programming could work in many different ways. Klingo in particular is the constraint solver that I'm using for answer set programming. And I didn't write Klingo, right? It's a thing that somebody else wrote. So I haven't looked at some of the I haven't looked at some of the internal details of how it deals with things like soft constraints. Cool. So there's probably some really good papers out there that you could find if you need those details. But the basic idea is that Klingo is written cleverly to not have to like restart all the time. It tries to backtrack very cleverly. It tries to do all sorts of clever constraint solving stuff that, you know, will do its best to optimize these soft constraints. And there's a lot of settings and things that you can parameterize in Klingo to make it work in slightly different ways. And I haven't finished playing around with all of that. So there's stuff that you can set that like makes it so that it produces more random results or things that are closer to your soft constraints. There's all sorts of stuff that you can do to kind of control Klingo. So
cool.
Definitely happy to look at that more later and talk to you more about it.
Thanks for giving the talk. Very informative. I definitely have more questions, but we're definitely out of time.
Thanks, Phil. All right, yeah, so if anybody has more questions, I will head over to the networking lounge and you're welcome to come and find me. And you can also ask me later on email or Twitter or something.